A Rankine cycle has an open feedwater heater operating at 1 megapascal. The steam generator outlet conditions are 8 megapascals and 520 degrees C. The condenser pressure is 30 kilopascals. The pumps are isentropic, but the turbines have efficiencies of 80%. The entrance to both pumps is a saturated liquid. What is the thermal efficiency of the cycle? So as with all Rankine cycle questions, a critical thing to understand from the beginning is what does the layout of the components look like from the description in the problem statement. So notice here we have a Rankine cycle and there is an open feedwater heater. There's no mention of any reheaters, so we assume we just have a single open feedwater heater. So a Rankine cycle with an open feedwater heater is going to look like this. So we'll just review these components. So coming out of the condenser at state point 1, we enter the first pump, and when we have an open feedwater heater, it's very important to understand you need 2 pumps. So the first pump pressurizes the water up to some intermediate pressure, the pressure that the open feedwater heater is operating at. So the feedwater enters the open feedwater heater, and there it mixes with some extracted steam. So that steam is extracted over here at point 6, partway through the expansion through the turbines. So we take a relatively large flow rate of cold water coming in here and a relatively small flow rate of hot steam coming in there, mix them together, and they leave the open feedwater heater. So this is how the open feedwater heater works. It preheats this feedwater before it gets to the steam generator by mixing it with some extracted steam from the turbines. So after those 2 streams mix together, they leave the feedwater heater here at 3 and then go into a second pump to pressurize this water all the way up to the steam generator pressure. Then it enters the steam generator, enters as superheated steam here, passes through the high pressure turbine, which we're calling turbine 1 here, produces work, and then a relatively small portion is extracted and the remaining steam goes through turbine 2 to produce more work. So very important that we know what the layout of components looks like for a Rankine cycle with an open feedwater heater. After we get this drawn, we would go through the problem statement and put all of the properties and all of the known information onto this diagram. So first of all, we know the condenser is operating at 30 kilopascals. We know the steam generator is operating at 8 megapascals, and so that's the 2 pressures that this Rankine cycle is operating between, the lowest pressure in the condenser and the highest pressure up in the steam generator. But there is an intermediate pressure here of 1 megapascal that the open feedwater heater is operating at. So notice that means the exit of turbine 1 is 1 megapascal, the inlet of turbine 2 is 1 megapascal. Likewise over here, the exit of the first pump is 1 megapascal, and the inlet to the second pump is 1 megapascal. So all of that is operating at 1 megapascal in this example. We're also told that the temperature at the exit of the steam generator is 520 degrees C. So notice the state is fixed there because we know the pressure, 8 megapascals, and the temperature, 520 degrees C. Other thing we're told is that the entrance to both pumps is a saturated liquid. So this is a very common assumption with Rankine cycles, that the exit of the condenser is a saturated liquid, and that's also the entrance to the first pump. This pump also has saturated liquid entering it. So both pumps have saturated liquid coming into them. In terms of the efficiency of these various components, the pumps are both isentropic, so the isentropic efficiency of the pumps is 100%, but the turbines have efficiencies of 80%, so the isentropic efficiency of both turbines is at 80%. Notice that we weren't given any information in this problem about mass flow rate, and we'll see how we deal with that as we go through the analysis. So to begin, what are we asked to find? Well, we're asked to find the thermal efficiency of this cycle. The assumptions we'll be making: steady state operation, adiabatic turbines and pumps, so no heat transfer with the surroundings in the turbines and pumps, reversible pumps, so we just reviewed that the isentropic efficiency of the pumps is 100%, so we are assuming they're reversible. The kinetic and potential energy are being neglected. And finally, constant pressure in the heat exchangers. So the condenser, the steam generator, and the open feedwater heater are all constant pressure devices. So we've been asked to find the thermal efficiency of this cycle. So to get started on the analysis, we certainly want to remember the definition of the thermal efficiency of any heat engine. And the Rankine cycle is just one type of heat engine. So it's the net work produced divided by the heat added from external to the cycle. So notice here we've written both the net work and the heat added as lowercase letters. So we'll be doing this analysis on a per unit mass basis. Now, as I said, it's a little bit more complicated here because the flow rate through the various components is not the same. So this is a Rankine cycle that has some branching. So we're going to go back to the diagram and talk about the contributions to the net work and the Q added of each of the components. So when we do this analysis, we're going to do it on the basis of the flow rate coming out of the steam generator. So if we think about every kilogram of steam that the steam generator produces, we want to figure out the work and heat transfer in the other components based on that flow rate. So notice all of the steam produced by the steam generator goes through turbine 1. There's no branching before turbine 1. So when we calculate a work transfer for turbine 1, we don't need to do anything to that. We can just keep that work per unit mass as it is. Notice that the second pump here also has the same flow rate as the steam generator because they're just connected directly with no branching. So the second pump, the steam generator, and the turbine all have full flow through them. Now, here's where the extraction happens. So for every kilogram of steam that comes out of this turbine, a small fraction of it is diverted for the open feedwater heater. So that means there's reduced flow in the second turbine, in the condenser, and in the first pump. So we need to account for that when we calculate the net work, because the work produced by this turbine and the work required by this pump will need to be reduced in order to recognize the reduced flow rate through them. So what we're going to do here is define a fraction y called the extraction fraction, which is the ratio of the mass flow rate in this line to the mass flow rate here. So it's essentially the fraction of the flow that is extracted here. So it's called the extraction fraction. So for this cycle, the mass flow rate is not the same in every component, and that's what we've just been discussing. If we say the fraction of the mass flow delivered by the steam generator, which is diverted to the open feedwater heater at point 6, is y, so that's our extraction fraction, then the mass fraction that passes through the second turbine, the condenser, and the first pump is 1 minus y. So if y turns the corner to head towards the feedwater heater, 1 minus y continues on to those components. So we have a reduced flow rate in the second turbine and the first pump. So the thermal efficiency of this cycle, we have Q steam generator in the denominator. The only place where heat is added is in the steam generator, and we don't have to multiply it by anything because it has full flow going through it. The net work in the numerator, turbine 1 and pump 2, we don't have to do anything with because the flow through them is the same as the flow through the steam generator. However, the second turbine and the first pump, we need to multiply by 1 minus y, or we need to derate the contribution of those to the net work. So we're doing all of these work and heat transfer calculations on the basis of per kilogram delivered by the steam generator. Now beyond this, it's a matter of using the first law of thermodynamics, our energy balance, to calculate these work heat transfers, and actually we'll also be using it to calculate the fraction extracted, because that was not given in the problem. We're going to have to figure out what that is. So now we set off to figure out all of the things on the right-hand side of this equation that we need. So conservation of energy for a control volume is what we'll be using. So here's our full equation. steady state, so that is gone. Depending on whether we're looking at a heat exchanger or a pump or a turbine, we will get rid of one of the heat transfer or the shaft work. We need to be careful with the summation. We're going to have to keep those around because when we analyze the Feedwater heater, it actually has two inlets. And finally, kinetic and potential energy are neglected everywhere in this system. So the first component we'll look at is the first turbine. And so for the first turbine, this tells us that the work produced per unit mass is H5 minus H6. So 0.5, the state is fixed because we know the pressure is 8 megapascals and the temperature is 520 degrees C. So table A4 would give us the value for the enthalpy, 3447.7 kilojoules per kilogram, and the value for the entropy, 6.7871 kilojoules per kilogram Kelvin. Now, what we need to do is consider the isentropic turbine first. Notice this particular turbine is not an isentropic turbine. It has an efficiency of 80%, but we need to first consider the isentropic turbine so that we have enough properties to evaluate the state at the exit. So the isentropic turbine will have an exit entropy the same as its entrance. So S6S will be equal to S5, and that's the value we just looked up here in table A4. So we go to table A4 now with that enthalpy and with the pressure there, which is 1 megapascal, and we get an enthalpy of 2873.8 kilojoules per kilogram. So we can go back and calculate the work of the turbine. So notice what we're doing here is I'm going to calculate the real work of the turbine by calculating its isentropic value and multiplying by the efficiency of the turbine. So the efficiency is 0.8 and H at the inlet is 3447.7 and the isentropic exit is our 2873.8 that we just looked up here. So this tells us that the work produced by the first turbine is 459.14 kilojoules per kilogram. Now before we leave that turbine, we have to find the value of H6. So this is the real enthalpy at the exit of the turbine. And we need that because we need to proceed on to looking at the next components. So notice we have a value for H6S, but that is not the real value of enthalpy at 0.6. So we need to get the real value of H6. Well, to do that, we just go back to our first law, and that's going to tell us that H6 is equal to H5 minus the work of turbine 1, and we have these numbers now, and so that's 3447.7 minus 459.14. So the enthalpy at the exit of the first turbine is 2988.6 kilojoules per kilogram. Now we can go on to the second turbine. So again, first law for the second turbine is H6 minus H7 on the right-hand side. The H6 we have, and this is why we found H6 here, because we need it for the second turbine. Now we're going to have to do the same thing with the second turbine as we did with the first one. We're going to have to first of all treat it as an isentropic turbine. So in order to do that, I need to find the entropy at 0.6. Well, I do know two properties at 0.6. I know the pressure is 1 megapascal and the enthalpy is 2988.6. So table A4 gives me an entropy of 7.0097 kilojoules per kilogram degree Kelvin. So that is the entropy at the inlet to the second turbine. So now we can look at the isentropic turbine, and we say that S7S is that same value that we just found, but down at 0.7 we also know the pressure is 30 kPa. So with the pressure and the entropy, table A3 will give us the enthalpy of the ideal exit of 2365.6. So we proceed much the way we did for the first turbine. We're going to be calculating the work for the second turbine as a product of its isentropic efficiency and its isentropic work. So the efficiency of that one is also 80%, and the enthalpy at the inlet and the exit are these values here. So the work per unit mass for the second turbine is 498.40. Now remember, that's actually the work per unit mass that actually goes through it. So we'll be multiplying that by 1 minus y when we calculate the thermal efficiency of the cycle. Now we're ready to look at one of the pumps. So we'll look at the first pump. So this is coming out of the condenser. Because it's a liquid pump, we can calculate the work directly from minus the integral of V dP. And the reason we can do that is because the fluid is liquid, the specific volume is very, very close to constant. So we can say this is just minus V1 times P2 minus P1. And therefore, we can go to point 1 where we know it's a saturated liquid at 30 kPa and get the properties from A3. So the specific volume, 0.0010223, and the enthalpy, 289.23 kilojoules per kilogram. So this allows us to calculate the work from the specific volume and the change in pressure. So that first pump is going from 30 kilopascals up to 1 megapascal. So that gives a pump of negative 0.99163 kilojoules per kilogram. Now we also need to apply the first law to the pump in order to get the enthalpy at the exit. So that's H2 for pump 1. And we need to do that because we're going to need H2 as we go on to analyze the next component. So H2 will be equal to H1 minus the work of the pump, which we just found. So the H1 that we looked up in the table a moment ago right here, and then the work that we just calculated directly from the integral of VdP will give us H2 of 290.22 kilojoules per kilogram. So notice H2 is just a little bit bigger than H1 because of the work that's done on the fluid by the pump. So now we can consider the feedwater heater. The first law applied to the feedwater heater says that the sum of the mass flow rates and the enthalpies at the two inlets minus the mass flow rate times the enthalpy at the exit all has to add up to 0. So that's because there's no work or heat transfer with the surroundings, and the kinetic and potential energies are 0. So 2 inlets and 1 exit. So if we take a look at this, so we actually have 3 mass flow rates in here, and we don't know any of those. So we need to learn how to deal with that. Well, first of all, realize that this m.6 refers to the extracted mass flow rate. If you look back on the schematic diagram, it's a bit ambiguous because point 6 is a junction. And I just want to be clear here, the m.6 in this equation refers to the flow rate that is extracted. So it's extracted between the two turbines, and it's one of the inlets to the open feedwater heater. So what we're going to do is divide this entire equation by m.3. So I'm going to divide the equation by m.3. So this just becomes H3. And then these other two flow rates, which are the two inlets to the feedwater heater, become ratios of two mass flow rates. So m.2 over m.3 plus m.6 over m.3. Now, this m.6 over m.3 we've actually talked about before. That's the extraction fraction, because this is the mass flow rate that is extracted, and this is the mass flow rate delivered by the steam generator. So we can replace this by y in this equation. Now, the other part here is actually 1 minus y, because whatever flow isn't extracted continues on to the other turbine. So earlier we defined our extraction fraction as m.6 over m.3. So we can rewrite this equation as 0 equals 1 minus y. So if this is y, this is 1 minus y times h2 plus y times h6 minus h3. So now the only unknown in this equation is y, the extraction fraction. So we can solve this equation for y, and it's h2 minus h3 divided by h2 minus h6. So the last of these enthalpies that we need to figure out is H3, and if you look back, point 3 is a saturated liquid at 1 megapascal. So table A3 will give us an enthalpy value for that of 762.81. So we can get our extraction fraction by putting those 4 enthalpy values in, and that works out to 0.17514. So 17.5% of the steam delivered by the steam generator is extracted between the two turbines. So the next component we're going to consider is the second pump. And again, because it's a liquid pump, we can calculate the work directly from minus the integral of V dP. So this becomes minus V3 times P4 minus P3. So we're assuming, because this is a liquid, that the specific volume doesn't change as we pressurize from 3 to 4. So at point 3, we have a saturated liquid at 1 megapascal. So table A3 gives us that specific volume of 0.0011273 meters cubed per kilogram. So we can calculate the work from that specific volume times the change in pressure, and realize pump 2 is going from 1 megapascal up to 8 megapascals. So that gives us a work of minus 7.8911 kilojoules per kilogram for pump 2. Now, before we leave pump 2, we also need to use the first law for that second pump to get the enthalpy at its exit. So H4 is equal to H3 minus the work of pump 2. H3 we looked up when we were working with the Feedwater heater, and the pump work we just calculated. So that tells us the enthalpy at the exit of the second pump is 770.7 kilojoules per kilogram. And the reason we needed to calculate that is because that's the inlet to the steam generator. So finally we can look at the steam generator, and the heat transfer into the steam generator will be H5 minus H4, and we have both of these enthalpy values from our previous work. So the heat transfer into the steam generator is 2,677.0 kilojoules per kilogram. So now we've calculated all of the work and heat transfers and the extraction fraction that we need to get the thermal efficiency. So we go back to our thermal efficiency expression, which we've repeated here, and we have all of these numbers available now. So we put all of those in. All of the work transfers in the numerator here are in kilojoules per kilogram as we calculated them, and as well the steam generator heat addition is in kilojoules per kilogram. So that will cancel out and we'll get a dimensionless number for the efficiency, which is 0.32183. And so our final conclusion, the thermal efficiency of the cycle is 32.1%.